and the first I mean the biasing all remains the same, right. So, it only makes sense to look at the incremental models of these amplifiers and see what effect the capacitances have on the performance of the amplifier. So, the simplest one is of course the common source amplifier. I am going to draw only the equivalent small signal equivalent. So, this is CGS, this is CGD, let us call that Vx, this is GMVx, this is RO, this is CDB, and this RO and RL I am going to club together into one resistance, load resistance RL, right, and this is VO. Okay. Now, how do we write so we can think of this, I am going to replace this as by it is not an equivalent. So, this is Vs by times Gs, where Gs is 1 by Rs. I am going to write everything in terms of conductances. So, this is Gs, this is GL, right, and I will be using Gs and GL interchangeably depending on what is more convenient to, right. So, there should be no confusion. Okay. So, how do we find VO? Well, we write the nodal equations and solve. Well, solve those KCL equations. Well, it is easiest done in matrix form. So, what are the unknowns that we are trying to find? We have two unknowns, Vx and Vo, and this is Gs times Vs and 0. All right. So, what are the terms in the matrix? Gs plus S times CGS plus CGD. All right. This is minus SCGD, minus SCGD, GL plus CGD plus CGD plus CDB. All right. Then where does GM show up? Which row will it show up and which column? First column. All right. So, what is VO therefore? Is nothing but you find the determinant of the matrix. Okay. So, this is basically GL plus S times CGD plus CDB times GS plus S times CGS plus CGD minus SCGD times GM minus SCGD plus, right? Yeah. Okay. And what is the numerator? GM minus SCGD times minus SCGD. Oh, sorry. Yeah, indeed. Times GS times VS. So, VO by VS therefore right. So, yeah, this is seems like a terribly boring exercise, but I am sorry I can't make it any more interesting. I will we'll solve the math and then we'll take a look at it and figure out why it makes intuitive sense. But before that, we have to actually do the algebra. So, please help me out here. So, the denominator, what all can we do? First thing, see, it's always easier to write it as DC gain multiplied by some. What is the DC gain? Sanity check, as S equal to 0, what should we get? I mean, look at the stare at the circuit. What should we get at S at DC? Minus GMRL. So, what we'd like to do is remove GM out of here and divide the denominator also by GM. All right. And similarly, so oh, sorry, actually, no, why should we do that? Sorry. I'll just move the GM outside here, and I will move GL out of the whole GS GL. I'll divide the denominator by GS GL. So this becomes 1 over GL. This becomes 1 over GS. This becomes GS GL. Okay. And therefore, the numerator I should get 1 over GL. So, this gives us nothing but minus GMRL times a numerator term which reduces to 1 when S equal to 0, and a denominator term which also reduces to 1 when S equal to 0. So, now let us simplify this stuff. So, this becomes 1 plus S times CGD by GL, CGD plus CDB times GL plus CGS plus CGD by GS, correct, plus S square times CGS plus CGD times CGD plus CDB over GSGL plus, I am going to collect the S terms here, plus CGD over GSGL. Sorry, have I missed something? I missed a factor somewhere, I think. Oh, this is GM minus SCD, is it? But we removed the GM common, isn't it? So, this must be, isn't this? Oh, sorry, sir. Okay. Sorry. All right. So, this is CGD times GM by GSGL. I hope this is okay. Dimensionally, it is consistent. Okay. And then you have to subtract minus S square CGD square over GSGL. God help us if you made a mistake. Okay. All right. So, this is this I am going to simplify this further. This is CGD plus this is CGD sorry there is a CGS times RS that's that term there, plus CGD times RS plus RL plus GM RL RS. Okay, so that basically takes care of these three terms, plus CDB times RL. Okay, so rather than do it this way, we can group terms as to with respect to RS. So, this basically is RS times CGS plus CGD times 1 plus GM RL plus RL times CGD plus C. Okay. Then what about the this term? Well, the denominator is common. Alright. So, if you multiply this out, you basically you see that the CGD square term gets cancelled. So, what you get is simply plus CGD CDB plus plus CDB CGS times RS. Does it make sense, folks? All right. So, this is the transfer function from the input to the output. So, let us see if we can make sense of these terms, right. I am going to draw the picture again. Let us go back to our original circuit, which is RS here, RL here, and this is Vs. Okay. So, now I mean there is no denying that this expression looks kind of very intimidating, right, the whole bunch of terms. Let us now stare at this expression and see if we can get any insight into why these terms make sense. First thing, what order transfer function do we have? It is a second order transfer function. First question is does this make sense? Why does it make sense? I mean, how many capacitors are there? There are 3 capacitors, but still the transfer function is second order. Is it likely that we made a mistake, or is it does that seem reasonable? So, you can see that even though there are 3 capacitors and you would normally expect the 3 reactive elements, you would normally expect to see a third order transfer function, but you can see that you have a 1 capacitor loop. So, all the 3 capacitors are not, all the 3 capacitor voltages are not independent, right. Once you specify one, the other 2 are, I mean the other 2 are, once 2 are specified, the third capacitor voltages. Basically the point is that even though there are 3 energy storage elements, you have 3 of them connected in a loop. So, all the 3 capacitor voltages are not independent, and therefore, it is still a second order system, right. And in fact, how many energy storage elements are there here? 2. What is the transfer function from input to output? It is a constant, right. So, you can see that the number of energy storage elements is not necessarily equal to the order, right. Okay. So, with that in mind, because there is one capacitor loop, it makes sense that the order of the denominator is second order, all right. Okay. So, the next question to ask is, is the system stable or not, right? Does this represent a stable transfer function? So, for a system to be stable, what comment can we make about the location of the poles? They must be in the left half S plane, all right. So, where are the poles, where are the location of the poles of this transfer function? Left half, why? All the coefficients of the denominator have the same sign, correct. So far we have understood why this minus GMRL makes sense, okay. We also understand why the denominator is of second order, and we also recognize that the system is stable, okay. Now, let us stare at the numerator. What comment can we make about the numerator? Where are the zeros? Yeah. So, basically you can say that the numerator, this is of the form 1 minus S over omega z, right, and this is now in the right half plane 0. So, is the right half plane 0 problematic for stability? Ralph, what do you think? No, right. The zeros can be anywhere in the S plane, and therefore, it's basically not a problem. Now, the question that we now have is, first of all, why is there a 0? So, let us take a look at the numerator and see why. First of all, what is the intuition behind? First of all, why is there a 0, right? And B, why is the 0 in the right half S plane, correct? Okay. So, in other words, can we stare at the circuit and basically say, why there is a 0 in a transfer function, in the transfer function? Okay, let me ask you another question. So, can any of you give me an example of an instance where zeros of a transfer function affect you in daily life? See, all of you own a phone, right, and you are sitting in the hostel, okay. Suddenly your friend calls you saying, hey, what happened, you owe me like 3,000 rupees, you borrowed it from me like long ago. Then suddenly what happens? Hey, sunai nahi de raha, signal is very bad, right, okay, and the call goes off, gets cut, right, all right. So, why do you think this is happening? And this always happens only when, most of the time, when you are inside a building, right, when you are in wide open space, this usually never happens, correct. So, why do you think this is happening? And what do you do if your signal is lost? What do you instinctively do? You just move your head this way, and suddenly you get signal and you can talk, right. So, what is going on? And remember, this only happens when you are among either when you are in a building, right. Usually it does not happen in wide open space. So, what is happening? So, it turns out that, so this is the base station, right. So, this is this is your hostel, and this is you in your hostel, right. And so, even if you are standing by the window, I mean, there is basically there's one path like that. There is also another path like that, and then perhaps this is your NIIT, so therefore there is some tree there, right. So, third path like that, and then on the tree there is a monkey, so it hits the monkey and then comes there is a fourth path like that, and so on. So, what you receive at your phone is basically you have signals from multiple paths. Each path has got its own delay and its own attenuation, I mean, to call it gain would be wrong, because I mean, you know, you are transmitting watts of power at the base station and you only receive a few microwatts, okay, at best, or you know, sometimes even picowatts, okay. So, so all these are all, you know, so each of these paths has got different attenuation factors and different delays, right. So, if you are at a point, it can so happen that the signal from all those paths interferes, you know, constructively, right, where therefore you get a huge, you get a, you know, a large signal, right, okay. Alternatively, it could also happen that all the paths basically interfere destructively, and therefore there is no signal there. You understand, right? And which is why you just, I mean, if you are not getting any signal, you just move, you know, a foot away, and then suddenly you get, the signal becomes all right. So, what is happening? How is it that that is possible? If you move slightly, what happens? The phase of each path now is different. See, for many numbers to add to 0, correct, those numbers must be related in a very special way, correct, okay. These are all complex numbers, because they are all, you know, magnitude and phase, correct. If there is a null at a certain point, it must so happen only when, you know, under some, you know, difficult conditions which are must be, you know, pretty difficult to achieve, correct, okay. But the moment you move away a little bit, that condition goes away, because the phases are all now completely different. So, you know, earlier they were cancelling perfectly, now they don't cancel so perfectly, and therefore that means that the signal you are receiving becomes higher, right. So, what is the moral of the story, and what does it have to do with our common source amplifier? When you are in an open field, this never happens. Why? There is only one path, all right, okay. So, so if you are in the Thar desert and you lose signal, right, that is not because there are 100 paths hitting your phone, right. If you are in the Thar desert and you lose signal, it is because you have entered Pakistan, that is all, you understand, right. There is no signal at all. Moving your head this way, that way will not help, okay, all right. So, what is the moral of the story? Therefore, you can have zeros when there are multiple paths from input to output. So, whenever you have a system where there are multiple paths from input to output, you will always have some complex frequency at which the signal from both these paths cancels, all right, okay. So, so with that background, now can you tell me why, can we intuitively see why there are zeros in the transfer function, and B, why the zeros are in the right half plane? Why are they zeros? There are two paths from the input to the output. How does signal get from the input to the output through two paths? One is through via Vx CGD, the other one is through GMVx, all right. So, since there are two paths, there is, you know, each path has some gain to the output, right. At some complex frequency, the two gains are equal and opposite, and therefore, you get a 0, correct. And now, so you can see that here the gain is a function of CGD, right, and here it is a function of minus GM, correct, because intuitively if I yank Vx up, through CGD, will this node tend to go up or go down? It will go up. If I through GM, what is GM trying to do? It is GM is trying to pull the voltage down, right. So, they are trying to do it in opposite directions, which is why you have a 0 in the right half phase, right. So, so basically the bottom line therefore is that it makes, I mean, now staring at the circuit, we see why we should expect to see a 0, because there are two paths for the signal from the input to the output. One is through CGD and one is through GM. Okay, and we also should be able to see why the 0 is in the right half edge plane, right? And that's because CGD is trying to, through CGD the output is is trying to go up, through GM the output is trying to go down. All right, so we understand this part. So in the next class we will take a look at the denominator and figure out whatever intuition we can from, and try to see why the individual terms in the denominator make any sense at all.